At the farthest conceivable boundary of instrumental perception, defining the absolute limit of the knowable, there exists a horizon not of matter, but of time. This is the observable universe, a perfect sphere centered not on any privileged location in the cosmos, but on the observer itself, extending in all directions for a distance now estimated at 46 billion light-years. This immense radius, far exceeding the 13.8 billion years of cosmic history, is not a contradiction, but a consequence of the metric expansion of space, the ceaseless stretching of the cosmic fabric that has carried the most distant, ancient galaxies far beyond the reach their initial light travel time would imply. This boundary is not a physical impediment, not a wall of crystal or fire, but rather a fundamental curtain of photon decoupling. It is the surface of last scattering, the precise moment, some 380,000 years after the primordial ignition, when the cosmos transitioned from an opaque incandescent plasma, a superheated fog of protons and electrons, to a transparent electrically neutral void. It was in this instant of clarification that photons were unbound, liberated to travel unimpeded across the emerging emptiness, carrying the fossilized imprint of that nascent structure. This ancient illumination, now cooled and stretched by cosmic expansion into the microwave spectrum, arrives today as the cosmic microwave background, an almost uniform whisper of radiation painting the entire sky. It is an echo of the universe's first light, and in looking toward it, we look not at a spatial edge, but at a temporal beginning. We see an impenetrable wall of our own past, a point beyond which the universe itself was opaque to the very light by which we see. This horizon is therefore an artifact of epistemology, a limit defined by the finite speed of light coacting with the finite age of the cosmos, representing the boundary of information, not the cessation of existence. Beyond this perceived temporal shore, the universe, according to all available evidence, simply continues. The structures we observe, the vast filaments of dark matter, the superclusters of galaxies, the cosmic voids measured in hundreds of millions of light-years, show no indication of diminishing toward this boundary. There is no thinning of matter, no change in the physical laws, no signature of a grand terminus. The cosmos appears, to the limits of our instrumentation, statistically uniform, isotropic, and homogeneous on the largest scales. This uniformity, the cosmological principle, is the bedrock upon which modern cosmology is built, suggesting that what we observe within our finite bubble of spacetime is a representative sample of a potentially much vaster, or even infinite whole. The question of an edge thus bifurcates. There is the edge we can see, the particle horizon, which is a boundary in time. Then there is the question of the ultimate physical edge. Does the entirety of spacetime, the manifold itself, have a limit? Does it stop? General relativity, the language of cosmic geometry, offers solutions where space itself can be finite yet possess no edge, no boundary. The simplest analogy, imperfect but instructive, is the two-dimensional surface of a sphere. An observer crawling upon this surface can travel infinitely in any direction without encountering a barrier, only to find themselves, eventually, return to their point of origin. The surface is finite in area, yet it is unbounded. If the universe possesses a sufficient density of mass and energy, its geometry would be positively curved, like this sphere, and it would be a finite self-closing system. In such a cosmos, a beam of light sent straight onward would, after traversing the circumference of space itself, return to its source. This concept of a finite, unbounded universe, however, finds itself challenged by the most precise measurements currently available. Cosmological data, particularly from the Planck satellite's mapping of the cosmic microwave background, indicates that the universe is, to the limits of observational certainty, geometrically flat. The angles of great cosmic triangles measured across billions of light-years sum to 180 degrees, just as they do on a flat Euclidean plane. This geometric flatness carries a profound implication. In the simplest models of cosmic topology, a flat universe is an infinite universe. It suggests a spatial manifold that extends eternally in all directions, a fabric without seam or limit, populated by an infinite number of galaxies, an infinite amount of energy, and an infinite array of possibilities. In this flat, infinite cosmos, the very concept of an edge becomes a semantic failing, a terrestrial limitation imposed upon a reality that has no need for containment. The horizon we observe is not the edge of the universe, but merely the edge of our view, a local artifact of light's finite travel time within an endless expanse. The galaxies we see receding near that boundary, their light shifted almost into oblivion, are not pressed against a physical wall. They are simply points in the infinite manifold whose ancient light is only now, after 13.8 billion years of travel across stretching space, reaching the terrestrial observer. Beyond them, an infinite ocean of other galaxies continues, their light still in transit, or perhaps locked in a race against expansion that it can never win. The mechanism driving this horizon, this separation of the knowable from the unknowable, is the expansion of spacetime itself. This expansion is not an explosion of matter into a pre-existing void, but rather the intrinsic stretching of the spatial fabric at every point. The equations of general relativity, when applied to a homogeneous and isotropic universe, demand that this fabric be dynamic, either contracting under its own gravity or expanding. Observation confirms the latter. The universe is expanding, and this expansion is accelerating. This metric expansion is the engine of cosmic separation. It inserts new space between galaxies, causing them to recede from one another. A galaxy 1 billion light-years away recedes at a certain speed, but a galaxy 2 billion light-years away recedes at twice that speed. This linear relationship, the Hubble-Lemaitre law, dictates that there must be a distance, the Hubble radius, at which the cumulative expansion of space between the observer and the distant object equals the speed of light. Galaxies beyond this point are not travelling through space faster than light, an impossibility, but rather the space between them and us is stretching so rapidly that their recession velocity exceeds c. Light emitted from such a galaxy, attempting to cross the gulf toward us, is like a runner on a treadmill that is accelerating. It is carried backward by the expansion faster than it can move forward. This creates a different kind of boundary, the event horizon. While the particle horizon is an edge in the past, defining what we can see, the event horizon is an edge in the future, defining what we will ever be able to see. Galaxies that cross this future boundary, swept away by the accelerating expansion driven by dark energy, are lost to us forever. Their light, emitted after that crossing, will never reach Earth, their part in our cosmic story concluded. Within this framework, the observer's position becomes fundamentally relative. The observational horizon, that 46 billion light-year sphere, is centered precisely on the Milky Way. This might imply a privileged position, a return to a pre-Copernican cosmology where Earth sits at the nucleus of existence. But this centrality is an illusion, a necessary artifact of observation. An observer in the Andromeda Galaxy would see their own observable horizon, a sphere of identical radius centered on them. An observer in a galaxy 10 billion light-years distant near the edge of our horizon would see their horizon, encompassing a vast volume of space, half of which is entirely inaccessible to us, lying beyond our temporal wall. Every point in the cosmos is the center of its own observable universe. This dismantles the very notion of a universal center or a universal edge. If the universe is infinite, this relativity holds absolutely. There is no center from which to measure, no boundary to approach. If the universe is finite and unbounded, like the sphere, the same principle holds. Every point on the surface is geometrically equivalent to every other, and no point can claim to be the center or edge of the surface. This realization is a profound decentering of the human perspective, placing the observer in a position that is simultaneously unique as the center of their own perceived reality, and utterly mundane, as just one of endless equivalent points in the cosmic manifold. The edge we perceive is a property of our interaction with spacetime, not a property of spacetime itself. It is a subjective, observer-dependent boundary, a horizon defined by the physics of information transmission in an expanding cosmos. The possibility of a truly infinite spatial extent, however, opens a conceptual chasm that strains against the limits of physical intuition. If the universe is geometrically flat and extends forever, it must contain an infinite amount of mass and energy. This implies the existence of an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. Within this infinite volume, every event with a non-zero probability must, given infinite opportunities, occur not just once, but an infinite number of times. In such a reality, somewhere beyond the horizon of our perception, beyond the limits of our particle horizon, there would be, statistical inevitability dictates, another solar system, another Earth, and another observer identical to the one perceiving this text. This concept, known as the cosmological multiverse or the patchwork quilt, arises directly from the marriage of a flat infinite geometry with the finite number of possible quantum configurations within any given volume of space, the Hubble volume. While the number of ways particles can be arranged is staggeringly large, it is not infinite. In an infinite universe, these arrangements must repeat. This is not a mystical conjecture, but a sober if unsettling consequence of applying finite probabilities to an infinite sample space. It suggests a cosmos of eternal recurrence, not in time, but in space, a vast tapestry where every conceivable history, every possible outcome, is physically realized somewhere in the endless, unseeable expanse beyond our temporal shore. This transforms the edge of our universe from a simple observational limit into a demarcation, a veil separating our unique observable history from an infinite sea of variations. This disquieting implication can be moderated, however, by a subtle distinction between geometry and topology. Our measurements confirm that the universe is locally flat, but this does not strictly necessitate that it is globally infinite. Topology, the study of properties preserved under continuous deformation, allows for geometries that are flat yet finite. Consider a two-dimensional sheet of paper, a flat Euclidean plane. If one rolls this sheet into a cylinder, it remains intrinsically flat. Lines drawn upon it still obey Euclidean geometry. Yet, it has a finite property in one dimension. Travel far enough, and one returns to the start. If one then connects the ends of the cylinder to form a torus, a donut shape, the surface remains intrinsically flat at every point, yet it is finite in both dimensions. Such a toroidal universe would be finite and unbounded, possessing no center and no edge, just like the sphere, but it would have a flat geometry. In this model, the universe could be much larger than our observable horizon, but not infinite. Light traversing this finite cosmos could eventually wrap around, creating the illusion of multiple, repeating images of the same distant galaxies. Searches for such repeating patterns in the cosmic microwave background have, to date, found no evidence, suggesting that if the universe is a finite topological construct, its scale is at least as large as the observable horizon itself. This leaves cosmologists in a state of precise ambiguity. The universe is either infinite or it is so colossally large and finite that its curvature or topological closure is currently indistinguishable from true infinity. The edge, in this context, remains elusive, pushed beyond the boundary of observation. Compounding this geometric uncertainty is the dominating influence of dark energy, the mysterious component driving the accelerating expansion of the cosmos. This acceleration, discovered in the late 1990s, fundamentally alters the long-term fate of the universe and redefines our relationship with its boundaries. Dark energy acts as a constant repulsive force embedded in the fabric of spacetime itself, a negative pressure that relentlessly pushes the universe apart at an ever-increasing rate. This acceleration creates the event horizon, the boundary of future causal contact. As galaxies are carried away by this accelerating expansion, they will eventually cross a point of no return. The space between us and them will stretch so fast that light emitted from them will never again be able to bridge the expanding gulf. They will fade from view, their redshift climbing toward infinity until they are rendered utterly undetectable. This process is already underway. We can currently observe galaxies that are, in the present moment, already receding from us faster than light, and are thus beyond our ability to ever visit, even though we can still see their ancient light. In the far distant future, as this acceleration continues, all galaxies not gravitationally bound to our own local group will cross this event horizon. The night sky, trillions of years hence, will be a place of profound emptiness, our own Milky Way Andromeda merged supergalaxy, appearing as a solitary island universe, adrift in an endless accelerating void, the light from all other structures having redshifted into oblivion. This accelerating expansion creates a final edge, a causal boundary that isolates our local reality, locking us within a diminishing bubble of knowable space, even if the universe as a whole is spatially infinite. The question, can the universe be infinite and still have an edge, thus resolves not into a simple affirmative or negative, but into a complex layering of definitions. The universe can be spatially infinite, a flat, endless expanse of energy and matter, and simultaneously possess a very real edge that is fundamental to our experience. This edge, the particle horizon, is not a physical barrier but a temporal one, defined by the age of the cosmos and the finite speed of light. It is the boundary of the observable, the surface of last scattering, the oldest light we can possibly detect. This edge is real, measurable, and defines the limits of our empirical science. Furthermore, the accelerating expansion of space-time creates another edge, the event horizon, a causal boundary in the future that defines the limits of any possible interaction, sealing off the vast majority of the infinite cosmos from us forever. The universe, in this model, is a paradoxical construction, a potentially infinite physical reality that is only accessible to any observer in a finite, time-bound, and ultimately shrinking causal patch. We are inhabitants of a finite island of knowledge defined by a past horizon of light and a future horizon of acceleration, adrift in an ocean that is, for all we can measure, functionally and physically infinite. The edge is not where the universe stops, but where our ability to perceive it and interact with it ceases. Ultimately, the human mind struggles to contain this dual reality. We are terrestrial creatures, evolved to perceive distinct boundaries, finite resources, and clear delineations between here and there. The cosmos, however, operates on a scale and under principles that defy this evolved intuition. It presents a reality where infinity is a plausible geometric state, and where edge is a relative observer-dependent phenomenon defined by the physics of information. The observable universe, the sphere of 46 billion light-years, is our home, our data set, the entirety of our empirical reality. We can model the geometry within this sphere with exquisite precision, and that precision points compellingly toward flatness, and therefore toward infinity. But we cannot prove it. We are epistemologically bound, trapped within our horizon. We cannot see beyond the cosmic microwave background because we are seeing the beginning of transparent time. We cannot know for certain if the universe wraps back on itself at a scale larger than our observational window. The satisfaction in cosmology comes not from a final, absolute answer to the question of the infinite, but from the cumulative comprehension of these nested scales. We have moved from a small cosmos centered on Earth to an immense expanding spacetime defined by relativity. We have identified our horizon not as a celestial sphere, but as a temporal boundary. We have discovered that our ultimate fate is likely one of increasing isolation due to an accelerating expansion. The edge, therefore, is real, but it is a property of time, light, and expansion. The infinity, if it exists, is the silent, unseen, and forever inaccessible context within which our finite observable drama unfolds.